Hello student, I am Dr. S. N. Munde, Assistant Professor Department of Mathematics, Sri RLT College of Science, Akola. So dear student, in previous lecture we have seen Cauchy estimate and some problems on a Cauchy estimate, or we can say that Cauchy inequality. Okay, so in this lecture we will see another point, that is power series representation of analytic function. Power series representation of an analytic function. So we will see first of all the statement of the power series representation of f of an analytic function, that is given as f be an analytic function in an open circle whose center a radius r. Then we have to prove that f of z equal to summation n equal to 1 to infinity a n z minus a to the power n for z minus a less than r. So this is the circle whose center a radius is capital R. So where a n equal to f n of a upon n factorial. So this series has a radius of convergence greater than equal to r. Okay. So this is the statement of the power series representation of analytic function. Now we will see the proof of this theorem. So what is we have given? So we have given f be an analytic function in an open circle whose center a and radius r. Okay, so let us we consider that this circle whose center a radius is capital R. So this is the outer circle and this is the inner circle. Okay, so this is open circle and this is a closed circle. So here f of z is an analytic in this open circle, and this is the closed circle, and this is the boundary of the outer circle. Okay, so let us we choose a small radius r such that 0 less than r less than capital R. Okay, तर या ठिकाणी आपण स्मॉल रेडियस अशी चूज करणार आहे की जी लाइज बिटवीन 0 टू r, कॅपिटल R पेक्षा छोटी असेल आणि 0 पेक्षा मोठी असेल. ओके, सो आपल्याला क्लोज बॉल मध्ये आपल्याला ते सिलेक्ट करावं लागणार आहे. So choose the small radius r such that 0 less than r less than capital R, so that closed circle whose center is radius r. So this can be also called as closed ball, which is containing in open circle whose center is radius r, or which is also called as a open circle, open ball. Okay, so therefore we can say that f of z is analytic on open circle, and therefore we can say that the f of z is analytic on a closed circle whose center is radius r, because f of z हा ओपन सर्कल वरती analytic असल्यामुळे आणि इनर सर्कल हे ओपन सर्कलच्या आतमध्ये असल्यामुळे आपण f of z या ठिकाणी f of z हा क्लोज सर्कल मध्ये सुद्धा पण analytic आहे. ठीक आहे. So therefore by using the Cauchy integral formula, f of z equal to 1 upon 2 pi r, this is the formula of Cauchy integral formula. Integral over gamma f of w upon w minus z dw for z minus a less than r, where gamma of t equal to a plus r e raised to power t, t lies between 0 to 2 pi. So let us we consider equation number 1. Okay, so to prove this theorem, let us we consider the term that is 1 upon w minus z, 1 upon w minus z, and this can be written as 1 upon w minus a, 1 upon 1 minus z minus a upon w minus a. Okay, so if you calculate or if you simplify this bracket and multiply this bracket, so you will get 1 upon w minus z. That means we can say that 1 upon w minus z can be written in this way. ठीक आहे, या ठिकाणी आपण 1 upon w minus z as it is लिहिलेलं आहे, फक्त अनदर फॉर्म मध्ये या ठिकाणी आपण लिहिलेलं आहे. Okay, if you calculate or if you solve this both term, you will get 1 upon w minus z. Okay, so left hand side 1 upon w minus z as it is 1 upon w minus a, and this is the power series. Sorry, this is the Gregory series. Okay, so summation n equal to 0 to infinity z minus a upon w minus a to the power n. Okay, so this is the geometric series, not a Gregory series, geometric series. Geometric series is given as 1 upon 1 minus r equal to summation r raised to power n, where n equal to 0 to infinity. If mod z minus a upon w minus a less than r. Okay, so then the geometric series can be written in this way. Okay, so but here mod z minus a upon w minus a less than 1. That means we can say that mod w minus a equal to r. Okay, this point which lies on a circle, and mod z minus a less than r. That means this point lies inside the circle. Okay, so as w lies on the circle and z lies inside the circle. Okay, so that means here we can say that the w which is lies on a circle and z lies inside the circle. Okay, so therefore by using this in equation number 1, then equation number 1 can be written as, put the value of 1 upon w minus z in equation number 1. So equation number 1 can be written as f of z equal to 1 upon 2 pi integral over gamma f of w upon w minus a summation n equal to 0 to infinity z minus a to upon w minus a to the power n dw for z minus a less than r. ओके, या ठिकाणी फक्त आपण 1 upon w minus z ची व्हॅल्यू इक्वेशन 1 मध्ये पुट अप केली आहे. ओके, so what are the next steps? So f of z as it is 1 upon 2 pi as it is. Okay, so we can write these steps. या ठिकाणी आपण f of w upon w minus a आतमध्ये घेऊया. So summation n equal to 0 to infinity f of w z minus a to the power n upon w minus a to the power n, and this one, that is n plus 1 dw, equation number 2. Okay, but we have given f of z is analytic on a closed circle whose center a and radius r. Okay, so therefore we can say that if the given function is analytic, then we can say that that function is a differential function and as well as continuous function, and also that function will be the bounded function and compact function. Okay, so therefore f is a continuous on a closed circle whose center a, radius r, and which is also compact in a closed circle. So therefore f is bounded on a closed circle center a, radius r. So therefore by using Cauchy estimate there exists m greater than 0 such that mod f of w less than equal to capital M. Okay, because w lies on a circle. Okay, so therefore by using Cauchy estimate mod f of w z minus a to the power n upon w minus a to the power n plus 1 equal to f of w. So this we will take the separate of the mod f of w upon w minus a mod z minus a upon w minus a to the power n. Okay, so f of w means that is less than equal to m. So this can be written as using this values minus f of w means capital M upon w minus a means this w lies on a circle, that is w minus a, that is r. Okay, mod z minus a upon w minus a to the power n. Okay, so here w which is belongs to curve gamma which is containing in a open circle, and mod w minus a equal to r. So let us consider equation number 3. But summation n equal to 0 to infinity mod z minus a upon w minus a to the power n converges as mod z minus a upon w minus a less than 1. Okay, so this term here converges to mod z minus a upon w minus a less than 1. So by using the geometric series, so therefore by Weierstrass M test, summation n equal to 0 to infinity mod f of w z minus a to the power n w minus a to the power n plus 1 converges uniformly on w, and mod z minus a less than r. If this converges to mod z minus a w minus a less than 1, so therefore we can, by using the Weierstrass M test, so this LHS side also converges to. Okay, so therefore equation number 2 becomes f of z equal to summation n equal to 0 to infinity 1 upon 2 pi I integral over gamma f of w upon w minus a to the power n plus 1 dw z minus a to the power n. Okay, equation number 4. Okay, so by using Cauchy higher order derivative formula, so this is nothing but the Cauchy higher order derivative formula. So fn of a higher order derivative formula is fn of a n factorial upon 2 pi integral over gamma f of w upon w minus a to the power n plus 1 dw for z minus a less than r. So we will put here, that is fn of a, by using fn of a upon n factorial. So by using this formula, so we can write uh, fn of a upon n factorial upon 1 upon 2 pi. So this is we can write in this way. So by using this formula in our equation, we get equation number 4, f of z equals summation n equals 0 to infinity fn of a upon n factorial z minus a to the power n, equation number 5. Okay, so here, so this term fn of a upon n factorial is independent of the w and z. So therefore we can say that, so this is a constant term and it is generated by the term an. So therefore an equal to fn of a upon n factorial for every n. So let us we use this in equation number 5. So this can be put up in equation number 5. Then equation number 5 can be written as f of z equal to summation n equals 0 to infinity an z minus a to the power n for z minus a less than r. Okay, so but here r can be chosen as a large. So r can be chosen as r less than capital R, that is mod z minus a less than capital R. Okay, so therefore RHS is convergent for the radius at least capital R. So therefore we can say this radius of the convergence is greater than equal to capital R. So this is the uh, complete proof of the given theorem. Okay, so now we will see the corollary. So this corollary depends on about theorems. What is the corollary? If f g to c is analytic and a belongs to g, then f of z equals summation n equals 0 to infinity a n z minus a to the power n for mod z minus a less than r, where r equal to degrees of a del g. Okay, so we can prove this theorem by using above theorem. So what is given? So here f g to c is an analytic and a belongs to g is any point which is in a region g, and r equal to degrees of a del g, which containing ball whose center a radius are containing in the region g. Okay, so therefore we can say that the f is the analytic on a open circle center a radius r. So where r is degree of a del g is a subset. Okay, so therefore by using the power series representation of an analytic function, so this can be written as f of z equal to summation n equals 0 to infinity a n z minus a to the power n for z minus a less than r. Okay, so here the term a n can be written as f n of a upon n factorial. Okay, so again by using the concept of the power series, so where r should be the chosen as a such that in a open circle, closed circle center radius r should be the subset of the g, because g is a region and open circle whose center a radius r which is containing in region g, and this closed circle which is containing in open circle. So therefore it is clear that the radius r will be the equal to the distance from the to boundary of g. Okay, so that is the radius equal to distance of a and del g. Okay, so this is the corollary of the uh, of this theorem, and this is another corollary. Okay, so this is corollary is again same as the above corollary. Okay, so in this way we have seen uh, theorem, that is a power series representation of the analytic function, and corollary. Okay, so in next lecture we will see the next point of this unit.